Sincere greeting to one and all. I am Tamanna from BSc Chemistry Honors second year. Today I am here with chapter Ether. Introduction. Ethers are a class of compounds having general formula ROR. The two R groups attached to the oxygen, which is called eternal oxygen, may be identical or different. Moreover, both these groups may be alkaline or both may be aryl, or one may be alkaline and other one aryl. Ethers in which the two R groups are identical are referred to as symmetrical or simple ethers, while those in which two are different are asymmetrical or mixed ethers. Thus, we have dimethyl ether is a symmetrical ether and methyl ether is an unsymmetrical ether. It may be recalled that ethers are functional isomers of monohydric alcohols, as the both have the same molecular formula C2H6O but different functional groups. Cyclic ethers, apart from ethers referred to above, ethers containing oxygen as a part of ring system are also known to be exist. They are known as cyclic ethers. For example, ethylene oxide, furan, tetrahydrofuran. Cyclic ethers containing three-membered ring are practically particularly important and are termed as epoxides. For example, ethylene oxide is the simplest epoxide. Cyclic ethers containing two or more oxygen atoms in a ring are also known to exist. Cyclic ethers which have four or more oxygen atoms in the ring are called crown ethers. They are generally named as X crown Y, where X is the total number of the atoms while Y is the number of oxygen atoms. For example, a cyclic ether having 12 atoms including 4 oxygen atoms known as 12 crown 4 is shown given below. Nomenclature of ethers. First, common system. Ethers are generally known by their names, which are assigned by adding the word ether after the names of alkali or alkyl groups present in the molecule as illustrated ahead. Dimethyl ether, ethyl isopropyl, ethyl phenyl ether. Second, IUPAC system. According to IUPAC system, ethers are treated as alkoxy RO derivatives of hydrocarbons. In case of unsymmetrical ethers, the R group having large number of carbon atoms is chosen as the parent hydrocarbon, while the other group along with oxygen is taken as alkoxy group. For example, methoxyethane. Second is 2-ethoxypentane, 2-methoxy-2-methylpropane, cyclohexane. Sometimes special names are used for some of the ethers. For example, anisole and phenethol. Common and IUPAC names of some ethers. Compound CH3O CH3, dimethyl ether or methyl ether, methoxymethane. C2H5O C2H5, diethyl ether or ethyl ether, ethoxyethane. CH3O C2H5, ethyl methyl ether, methoxyethane. CH3O2 CH3 methyl isopropyl ether, 2-methoxyoxypropane. CH3CH2OCH double bond CH2, ethyl vinyl ether, ethoxyethane. Benzene O benzene, diphenyl ether or phenyl ether, phenyloxybenzene. Benzene OCH3, methyl phenyl ether, methoxybenzene. Benzene OC2H5, ethyl phenyl ether, ethoxybenzene. Problems. Write IUPAC name of the following compounds: first, second, third, fourth. First one is 1-ethoxy-2-methylpropane. Second, the given formula may be written as and its answer is 2-methoxypentane. Third one is 1-methoxypropane. Fourth one is 4-methoxycyclohexane. Method for formation of ethers. Ether may be prepared by the following methods. First, Williamson synthesis. This is easily the most important and wide used for the preparation of both symmetrical and unsymmetrical ethers. It is carried out by treating an alkyl or substituted alkyl halide with sodium alkoxide or sodium pentoxide. Sodium alkoxide with R-X gives to ROR- plus NaX. Sodium phenoxide plus Rx gives to benzene OR plus NaX. For example, sodium ethoxide plus ethylene iodide is ethyl ether. Sodium ethoxide methyl bromide gives to ethyl methyl ether, and sodium phenoxide plus ethyl iodide gives to phenolphthalein. Mechanism. The reaction involves nucleophilic substitution of alkoxide or phenoxide ions for the halide ions of alkyl halide, that is RONA in equilibrium, RO negative plus Na positive, RO having lone pairs and negative charge on O, plus R-X slightly positive charge on R and slightly negative charge on X gives to ROR- plus X negative. For the preparation of methyl aryl ether, methyl sulfate CH3 twice SO4 is generally used in place of methyl halide. For example, sodium phenoxide plus methyl sulfate gives to 2 moles of anisole and Na2SO4. Limitations of Williamson synthesis. The choice of alkyl halide and sodium haloxide to be used in a Williamson synthesis is somewhat restricted because of the following considerations. First, since a halogen attached to an aromatic ring cannot be readily replaced by a nucleophilic reagent, aryl halide are not generally used in the Williamson synthesis. Therefore, in the preparation of alkyl aryl ethers, the reaction is carried out between an alkyl halide and sodium phenoxide and not between aryl halide and sodium alkoxide. For example, as shown below, phenethdol is prepared by reaction between ethyl iodide and sodium phenoxide and not between phenyl iodide and sodium ethoxide. Sodium phenoxide plus C2H55 gives to phenol plus NaI. Diaryl ethers are not generally prepared by these reactions. However, they can be obtained by reaction of an aryl halide and sodium with sodium phenoxide at high temperature in the presence of copper. For example, sodium phenoxide plus bromobenzene in presence of copper 583 temperature 6 to 603 Kelvin gives to phenyl ether plus NaBr. Second, as the Williamson synthesis involves the attack of strongly nucleophilic alkoxide or phenoxide ion at which alkyl halide elimination can also take place as a competing reaction to substituent. Now, tertiary alkyl halide have greater tendency to undergo elimination than secondary or primary alkyl halide. Therefore, in the preparation of unsymmetrical ethers where there is a choice of alkoxide and alkyl halides, one should select the alkyl halide that has a greater tendency to take part in substitution and smaller tendency to undergo elimination. Therefore, primary alkyl halide which have the least tendency to undergo elimination are used in preference to secondary alkyl halide, which is drawn are preferred to tertiary halides. On other hand, tertiary alkoxide are preferred to secondary or primary alkoxide. For example, in preparation of ethyl tertiary butyl ether, we employ ethyl halides and sodium tertiary butoxide and not tertiary butyl halide and sodium ethoxide. Second, by heating alkyl halide with dry silver oxide. Simple but not mixed ethers can also be prepared by heating alkyl halide with dry silver oxide. For example, ethyl iodide reacts with Ag2O, gives ethylene ether plus 2 moles of AgI. Third, by the dehydration of alcohols. When an excess of alcohol is heated with concentrated sulfuric acid or glacially phosphorus acid at suitable temperature, 2 moles of alcohol lose 1 mole of water to form a symmetrical ether. Thus, we have 2 ROH in presence of sulfuric acid. Suitable temperature gives 2 ROR and plus H2. For example, ethyl alcohol gives 2 ethyl ether plus H2O in presence of sulfuric acid at 413 degree Kelvin temperature. Note: the preparations of ether from alcohol is always accompanied by the formation of alkenes due to the complete dehydration of alcohols. In case of primary alcohols, alkenes are formed only in small amounts, which can be further suppressed by using alcohol in large excess. In case of secondary alcohol, alkenes are formed in relatively large amounts. In case of tertiary alcohol, alkenes become the main product in place of ethers. And therefore, dehydration of alcohol is used for preparing ethers for primary alcohol. Mechanism: the mechanism of formation of ethers involve nucleophilic substitution with the oxonium ion as a substrate and second molecule of alcohol as nucleophile. The reaction can follow either first order kinetics SN1 mechanism or second order kinetics SN2 depending upon the nature of the alcohol used. In generally, secondary and tertiary alcohols react by SN1 mechanism, while reaction of primary alcohol follow SN2 mechanism. In both the mechanisms, the first steps involve the formation of oxonium ion. This is followed by other steps which of course differ in two mechanisms as is illustrated ahead. SN1 mechanism is shown. ROH plus H positive gives to RO lone pair plus H oxonium ion or protonated alcohol. Then the ROH slow reaction will take place, gives carbocation and water. Then the oxonium ion will react with the carbocation and give oxonium ion or protonated ether. Fourth step involves the protonated ether. Fast reaction will go and ether will produce plus H positive will release from the reaction. Similarly, in SN2 mechanism, alcohol will react with H positive ion which is from the acid gives to ammonium oxonium ion or protonated alcohol. In next step, the ether will produce a transition state or protonated state. Then the removal of water will take place and oxonium ion will produce. After that, the oxonium ion will carry the reaction and forms ether plus release H positive ion. The dehydration of alcohol may also be carried out by passing the vapors of alcohols over a catalyst like alumina at suitable temperature. For example, 2C2H5OH in presence of Al2O3 523 Kelvin C2H5O C2H5 plus H2. Limitations of method. First, dehydration of alcohol cannot be used for the preparation of unsymmetrical ethers as it leads to the formation of complex mixtures. Second, it cannot be used for the preparation of ethers from secondary and tertiary alcohol because it leads to the formation of alkene in large quantities due to the complete dehydration of alcohol. The third, the temperature of the reaction has to be carefully controlled to avoid complete dehydration of alcohol. Preparation of methyl ether by the use of di- diazomethane in the presence of fluoro fluororobic acid. Diazomethane react with alcohols or phenols to yield methyl ethers in excellent yields. For example, N-hexyl alcohol C6H13OH is easily converted into hexyl methyl ether by this method. reaction of an hexyl alcohol plus diazomethane in presence of HB4 gives to an hexyl methyl ether. The mechanism is as follows. Fifth, alkoxymercuration and demercuration of alkene. Oxymercuration and demercuration reaction for the conversion of alkenes into alcohols can also be extended for the preparation of ethers from alkenes. For preparing alcohols, oxymercuration of alkenes is carried out in water followed by demercuration with NaBH4. For the preparation of ethers, alkene is treated with alcohol in the presence of mercuric acetate followed by demercuration with NaBH4. The procedure is known as oxymercuration and demercuration, and it is net result in addition of alcohol to alkene to the form ether in accordance with Markovnikov's rule. For example, the overall reaction for preparing ethyl isopropyl ether from propane may be shown as the follows. Propene in presence of HgOC, OAC twice or CH3CH2OH, and second is NaBH4 gives to ethyl isopropyl ether. 6. By the addition of alcohols to alkenes, direct addition of alcohols to alkene in the presence of suitable mineral acid can also be used for the preparation of mixed ether in particular. For example, 2-methyl-2-propyne plus CH3OH in presence of sulfuric acid gives to tertiary butyl methyl ether. Physical properties. Ether can be regarded as organic derivatives of water in which the hydrogen atoms have been replaced by alkyl group. Like water, the oxygen atom sp3 hybridized in ethers is surrounded by two lone pairs and two bond pair of electrons. As such, ethers are bent molecules in which the COC angle is nearly tetrahedral. However, the actual angle depends upon the size of group attached to oxygen. For example, the COC. Here the CH3 have a bond angle 112 degree. An angle is dimethyl ether is 112 degree, while in diethyl ether the angle is 118 degree. As the size of alkyl group increases, the steric repulsive interactions push the groups apart so that the bond angle increases. The molecules of ethers are weakly polar with oxygen having a partial negative charge, and each of these of the attached carbon having a slit positive charge. Due to the bent shape of their molecules, the dipole moment of one CO bond does not cancel out the dipole moment of the other bond. The net result is that ether possesses a small net dipole moment. Example, diethylene ether has dipole moment 1.18 diopter. The physical property of ethers are as follows. First, physical state. Except methyl ether and ethyl ether, which are gas at ordinary temperature, all other ethers are colorless, volatile, and pleasant smell liquids. They are highly inflammable. Second, boiling point. The weak polarity of ethers does not affect their boiling points significantly, so that their boiling points are close to those of alkanes with similar molecular weightage, but their boiling point are much lower than those of corresponding alcohols due to the absence of hydrogen bond between ether molecules. Amongst themselves, the melting point and boiling point of ether increases with increase in their molecular masses. Third, solubility. Ethers are freely soluble in organic solvents, although they dissolve in water also to an appreciable extent. This solubility in water is probably due to the formation of hydrogen bonds between water and ether molecule. Ethers are very good solvent themselves. Fourth, density. They are all lighter than water, although the density increases with increase in molecular mass. Chemical properties. Ethers are relatively unreactive compounds. They are stable towards active metals, alkalis, oxidizing agents, and reducing agents. However, they do undergo the following reactions. First, formation of oxonium salt. Basic character. Ether dissolve in concentrated solutions of strong minerals acid to form oxonium salt. In this reaction, ethers behave as Lewis bases due to the presence of two lone pairs of electrons on oxygen. Thus, we have, for example, ROR plus HCl gives to dialkyl oxonium chloride, and then dimethyl R CH3O CH3 plus HCl gives to dimethyl oxonium chloride. CH2H5 CH2H5 C2H5O C2H5 plus H2SO4 gives to diethyl oxonium hydrogen sulfate. The salts are stable at low temperature in strongly acidic medium. However, they get decomposed by water to give ethyl back ether and as the acid. Second, formation of coordination complexes. Being Lewis bases, ethers are forms coordination complexes with Lewis acids such as BF3 and AlCl3, and also combine with Grignard reagent. For example, Ca2H5O C2H5 plus BF3 gives to boron trifluoride ethyrate. 2 moles of C2H5O C2H5 plus R MgX gives to Grignard reagents ethyrate. Third, formation of peroxide auto-oxidation. On standing in air or oxygen, particularly in the presence of light, ethers are readily oxide to the form peroxides. The structure and composition of ether peroxides are also known with certainty. One of the proposed structure is shown below. In case of ethyl ether pentoxide, ethyl ether plus O2 gives to ethyl ether peroxide. The ether peroxide are unstable compounds and decomposes exclusively when heated. Their presence in ether can be detected by the formation of a red color on shaking the ether with an aqueous solution of furious ammonium sulfate and potassium thiocyanate. Ethers must be made free of peroxides before being distilled. This can be achieved by washing the ethers with furious sulfate solution or distillation over concentrated sulfuric acid. Fourth, cleavage by halogen acid. On heating with equimolar amount of concentrated halogen acid, particularly hydroid acid or hydrobromic acid, the ether linkage breaks to form an alcohol or phenol and alkyl halide. For example, ethyl ether gives ethyl iodide and ethyl alcohol. The reactivity order of halogen acid in the reaction is is more reactive than HBr than HCl. In the presence of acid, the alcohol first form react with another molecule of halogen to form alkyl halide. Thus, in that case, the overall reaction may be depicted as ROR dash plus 2 moles of HX gives to RX plus R dash X plus H2. Mechanism. The mechanism of the reaction is believed to be as follows. First, initially the ethers react with acid to form an oxonium ion and or protonated ether as shown ahead. Second, the oxonium ion is then attacked by the nucleophilic halide ion by SN1 or SN2 mechanism depending upon the nature of R and R dash groups. The reaction conditions. Presence of primary alkyl group favors SN2 mechanism, whereas secondary or tertiary alkyl group tends to react by SN1 mechanism. Thus, we have SN1 mechanism, RO H R dash low reaction, R positive plus R dash OH, R positive plus X negative gives fast reaction RX. SN2 mechanism, X negative ROH R dash gives a transition state and then gives RX plus R dash OX. Point of cleavages. In case of mixed ethers, the alkyl halide produced depending upon the nature of groups attached to oxygen. First, in the cleavage of mixed dialkyl ethers, the alkyl halides is in general obtained from the smaller alkyl groups. For example, CH3O C2H5 plus H positive gives to CH3I plus C2H5OH. It can also be explained on the assumptions that the mechanism involves in the case of SN2 because of the steric effect of large group X negative ion attacks the smaller methyl group. Second, when the ether contain a primary or secondary alkyl group and tertiary alkyl group, we get a tertiary alkyl halide. For example, methyl tertiary butyl ether gives to tertiary butyl iodide plus CH3OH. This can be explained by SN1 mechanism. The tertiary carbocation, being more stable, is produced in presence of primary or secondary carbocation. This leads to the formation of three tertiary alkyl halide. Third, cleavage of alkyl aryl or diaryl ethers. In case of alkyl aryl ethers, the cleavage of aromatic carbon-oxygen bond is much more difficult than the cleavage of alkyl carbon oxygen bond, and thus the cleavage of such ethers by halogen acid yields a phenol and an alkyl halide. For example, anisole plus Hi gives to phenol plus CH3I. The phenol is not converted to iodobenzene. Even the excess of hydrogen iodide diaryl ethers are very difficult to cleavage as both carbon attack to the oxygen are the part of aromatic rings. For example, phenyl ether is not cleaved by Hi even at 525 temperature Kelvin. Zissel method. Cleavage of alkyl aryl ether with hydroiodic acid forms the basis of Zissel's method for the estimation of alkoxy groups such as methoxy or ethoxy. In such ether, a known weight of the compound is treated with excess of concentrated hydroiodic acid. The alkyl iodide, methyl iodide, or ethyl iodide formed through cleavage is treated with alcoholic silver nitrate solution. The participate of silver iodide produced is weighed from the amount of silver iodide formed. The percentage of alkoxy group is estimated. Fifth, cleavage with sulfuric acid. When heated with dilute H2SO4 under pressure, ether undergo cleavage and get hydrolyzed into alcohol. ROR plus H2 gives in presence of dilute H2SO4 and heat and pressure gives 2 moles of ROH alcohol. On heating with concentrated H2SO4, ether react in the same manner as with halogen acids to form alkyl hydrogen sulfate and alcohol. For example, C2H5O plus H2SO4 gives ethyl hydrogen sulfate or plus C2H5OH ethanol. 6. Halogenation. On treatment with halogens in presence of sunlight, ethers are readily halogenated to form polyhalogenated ethers. For example, C2H5O, C2H5O ethyl ether, Cl in presence of Cl2 and light gives perchloride chloroethyl ether. If the reaction is carried out in the absence of sunlight, halogenation takes place at the alpha position only. For example, CH3, C2O, C2, CH3 in presence of Cl2 in absence of sunlight gives alpha dash dichloro dimethyl ether. 7th, electrophilic substitution. Beside the characteristics reaction of ethers described by above, aromatic ethers such as anisole and pentanol undergo aromatic electrophilic substitution like nitration, halogenation, etc. It may be recalled that the alkoxy group is moderately actively and orthopara directing. For example, first nitration, anisole plus HNO3 gives to H in presence of H2SO4. Removal of H2O molecule gives orthopara nitroanisole Sol. Second halogenation. Anisole gives in presence of Br2SES2 gives to ortho and para bromo anisols. Explanation. Due to the net electron releasing result as of its I negative electron withdrawing inductive effect and M plus M electron releasing resonance effect, the alkoxy group increases the electron density around aromatic ring and thus stabilize the intermediate carbocation. Thus leads to the faster electrophilic substitution. The orthopara directing effects may be explained in terms of contributing. The orthoparadictic effect may be explained in terms of contributing structures of the carbocations formed by attack of electrophilic, say E positive or orthopara meta positions as shown below. Ortho attack is more stable than para is also more stable meta attack. It is It is apparent that the carbocation formed by ortho and para attack are more stable than the meta carbocation due to the addition contribution by particular stable contributing structures, first D and second D respectively, in which each atom except hydrogen has a complete octet of electrons. As a result, the ortho and para carbocation are formed in presence of meta ions, so the substitution occurs mostly at ortho para positions. Here there are two problems. How do you justify the boiling point of dimethyl ether is somewhat the more than that of propane but lesser than that of ethanol? Second is, name the alkyl halide and sodium alkoxide used in the preparation of ethyl tertiary butyl ether. Yes, I am done. Thank you.